Hello, it's been a little while since I've done any scatter tutorials, and in this one I just wanted to highlight a few of the new features of scatter that Rob has developed over the last year or so. It's going to be slightly different, this tutorial, because it's not going to stand alone. I'm going to mention odd features and it might feel as though I'm sort of rushing through and not being very clear on how everything fits together. The features that I'm going to talk about are in other tutorials. So there's a tutorial on reducing sex-ax data. This is going to give all of the information about how to do that, and I'm just going to talk about one or two additional points to do with that. And then there's a tutorial on the initial assessment of data quality, and again this is going to have a lot of the information that you need. I'm just going to randomly highlight a few extra issues. Okay, so we're going to start off doing HPLC data reduction in the subtract tab. It used to be that you would choose the first file in 600 images from an HPLC run. You'd have to sort of scroll all the way down to the bottom, hold down Shift and select a window, and then scroll all the way back to the top, grab the first one and drag it into the samples list. You don't have to do that anymore. It can be a bit cumbersome to do. Now there's this new option, build list from file. I check that button, okay, and then I just take one file from my list and drag it in, and you can see loading files and off it goes. So what it's done is it's looked at the unique parts of the file and the parts that are varying, and it's used it to automatically build the file list, which can be pretty useful to do. You can see it's loading the files in. So that's really useful. I'm just going to show the next feature, I'm just going to very quickly run through the HPLC data reduction. So trace, we get our trace. This looks horrendous, but this is just for an example. I've chosen a buffer region, I've chosen the region of interest, set range, I do signal plot again, I decide on a threshold, I add RG to the signal plot, I do signal plot again, I choose the region that I want to average together, give it a file name and subtract. And it's finished. Okay. Now the thing I wanted to show you is this sax directory here is the one that I've set as the output directory, and if we look at the most recent files you can see we've got this average and median, which is the output from this HPLC analysis. We've also got bsa.pdf, it's called BSA because that's the file name I gave, and if I open this up you will see that it's a PDF kind of report of what I just did. We've got the full trace, we've got a whole lot of overlapping images from that window that I selected. This Durbin-Watson and Shapiro-Wilks test, these relate to a sort of a statistical analysis of how the scattering signal is varying within the window that I selected. So you can imagine here if there's a real direction to this. So you start off with the first image and then the second image is very different, and then the next one different again. You would see a sort of a direction to these statistics. For Durbin-Watson, the measure of perfectly random is, perfectly the same from a statistical point of view, a score of 2. And so, we're really kind of varying about this. There's maybe a bit of directionality to it, but anyway, this is just a quick look to see if they're the same. We've got I0 and RG within that window. Here's my average and median files. There's a little kind of figure legend that you could use in a paper at the bottom, and there's a kind of a breakdown per frame of some of the parameters here. So just a nice little PDF report. I'll talk more about the PDF reports in a little while. Okay. So here we've got the file that I just put out, BSA average. We've been doing the Guinier analysis like this. You can see it's a nice straight line fit in the Guinier all the way out to 1.3. Q times RG 1.3. So that's lovely. We know that BSA exists in solution as a monomer, a dimer, a tetramer. So the HPLC run, we get rid of all that complexity, but these were measured in the batch mode using the Biosax robot, and you can see that they're quite a lot worse. That's why we have this sort of curved shaped fit in the Guinier. What I showed before was that we were truncating from this end and going back and just fitting the Guinier in this region here. But with the Guinier peak analysis, it's a little bit like the normalized Kratky in that it should be coming in to where the crosshairs are. And you can see when we do the Guinier fit down here, the data is sitting significantly above where it should be. Okay, so one way we can deal with that is if we start getting rid of data from the bottom. You can see, effectively when you get these kind of smile-shaped residuals, I could either truncate back from one end and just fit the data here, or I could truncate from this end and just fit the data here, and I would get two different RG values, and what is the right thing to do? And this is giving you a clue. So really what we should be doing is I cut from the the small angle end. You can see we're actually getting closer and closer to the crosshairs here. And as I come out, because RG is dropping, this Q times RG limits are going down as well. So I'm going to put this back up to 1.3 like this. Okay, now you can see actually we've still got a bit of a smile shape in the residuals here, so I'm just going to get rid of a few more points. Probably this is a better measurement of RG than when we did it the other way around, because this is now sitting on these crosshairs. So that's a good way of using this Guinier peak analysis. It's deciding which end do I crop from in my Guinier fit. Okay, that's not a new feature, it's something that I've realised that I didn't realise before. So that's quite useful. Obviously this is a mixture, so we're taking everything with a pinch of salt anyway. Okay, so I'm going to come back to this again. There's once you've done all the analysis and you've got RGs and I0s in here, there's one of the options which is really difficult to see, but is this PDF option. You can click that, give it a file name, you can give it a figure title, you can say, this is some data, what I measured, etc., my figure, and then you can go save, and we get a report here, and you can see I only had one image selected up here, so it's just made a report of that image. Had I selected multiples and done PDF, save, we get everything in the report. So it's quite a useful way of outputting these PDF files. You can also, if you right mouse click on a file, you can do, where is it? Create report from a single data set, and that will also output that that PDF file. Okay, Right, so the last thing that I wanted to highlight in this tutorial, and this is the feature that's I'm sure going to make you very enthusiastic. One of the big challenges is how do we do the P of R function, how do we choose Dmax? That is covered in the real space P of R tutorial. And many of you will have found that to be quite difficult. So Rob has this lovely feature now, find Dmax. I can hear you all stopping breathing at this point. So here we go. What have we got? We've got, this is the VC plot. If you remember, I mentioned it in the data analysis tutorial. It's really giving us a look at how good our buffer matching is and how the signal, the scattering signal, how far out it goes in Q space. And what we're looking for is a sort of a saturation function that comes over. So this line is an attempt to estimate where your scattering signal runs out. And it's saying that a suggested Q max would be 0.24. So what that means is when we eventually go through to the real space P of R fitting, we should probably start by truncating the data back to 0.24. Use your common sense a little bit with this. But then we're going to do a search for the what the Dmax should be. Now, for BSA, we normally set the Dmax at around sort of 95 to 100 angstroms. I'm just going to restrict this range a little bit. So I'm going to say somewhere between 80 and 120. You can leave it a wide range if you like. It's just that if I restrict it, it's going to go a little bit faster for this tutorial. I'll probably use this method for calculating Dmax here. Okay, so then I say all right, and you can see it's having a think. So basically what it's doing is it's doing exactly what you would do by eye. It's looking at the smoothness of the function. It's looking at how slowly, or how smoothly it approaches the line. It's doing some statistical analyses and things, and you can see here the most likely Dmax is 98.5. So what this is a sort of a likelihood score. So as we go between 80 and 120, you can see that there's some complexity here, but this is the most likely Dmax, and that's what it's chosen. If this function here, the likelihood score, doesn't really show a peak, or it shows multiple peaks, it's possible that your Dmax isn't well resolved. But in this case, what we've learned from this tool is that the suggested Q max is 0.24 and that the likely Dmax is 98.5. Okay. Oh, I've just triggered that again. Let me cancel that. Okay, so what we do next is real space. We know Dmax here should be 98.5, and the Q max should be 0.24. That was a lucky guess, by the way. So that's it. Now you can also see that Rob has added in a whole bunch of different methods for calculating P of R. I'm not going to go in here to a lot of detail on what these are, but there's a couple of functions that are quite useful here. One is background. So what that's going to do is have an attempt at estimating a sort of a background correction, and that can often help here. There's also positive only, and that just takes out anything that's kind of negative. You can see this isn't fantastic here. Maybe the data is not ideal, but anyway, so that's the P of R. Generally speaking, with these different options, the advice at the moment is start on the left-hand side and kind of work your way along if things aren't working. The background and positive only functions aren't available for all of these. So if I go to Legendre you'll see it's sort of taken these off, and if I try and apply the positive only, it flicks back to the L1 norm because the Legendre doesn't support the use of the positive only, and and so on. Yeah, so I think positive only is only for the L1 norm. So anyway, that is the new features in scatter, and I hope that made sense.